Okay, we need to come out with the ODE equation or ODE model for the system, right? Once we get the ODE, transform into Laplace form. Okay, we also have discussed about this. We already look onto the table on how to use common function from time function into Laplace form, right? And then number 3 is to apply initial condition. Right, so given any initial condition in the system, like for example here, given k equal to 1, c equal to 1, and then also x0 equal to 0. Okay, so we're going to apply that into the initial condition. Okay, that has been illustrated in example spring damper system. All right, after we apply initial condition, we're going to apply input signal. Right, so it depends on the type of the input signal, whether it is step input, sinusoidal input, ramp input, or impulse input. Okay, so and of course the input signal must also be in the Laplace form. Okay, number 5 is to do partial fraction decomposition. Okay, so after we apply the input signal, we're going to do the partial fraction decomposition based on the Laplace equation. Okay, the objective is to solve for parameters in the Laplace in the Laplace form there. Okay, so we convert into partial fraction decomposition. So therefore, we need to solve for whether it is A, B, C, or D. Okay, I believe we're going to look onto partial fraction today. And last one is after we have solved for the parameter in partial fraction, we're going to do the inverse Laplace. Okay, so this one will give you function in time. Okay, whether it is ft, yt, the output, meaning that the output with function of a time. Okay, this is what we call as time response. Okay, so we're going to see the response of the output when the time is changing. Okay. All right, so basically we have looked onto how to produce ODE. Okay, and then we also look onto apply Laplace form. Okay, transform into Laplace form. Okay, apply initial condition and apply the input signal. Okay, and today we're going to look onto the partial fraction decomposition. All right. Okay, let's do example number 1 here, following the step that we have discussed just now. Okay. Right, find the time response x naught t. Okay, the output in function of time. Oh, sorry. Let me record first. All right, let's start with example number 1 here. Okay, so let's find the time response x naught t. Okay, because the output is x naught and the input is xi. For unit step input, xi t equal to 1. Okay, meaning here it is unit step input. Okay, it is unit step input. Okay. The with initial condition x naught 0 is 0 and x prime not 0 equal to 0, and then take ratio of k over m equal to 2 and c over m equal to 3. All right. I believe you already derived for this equation. Is it? Derive. Okay. Okay, if you refer to example number 1, we already derived the ODE for the system. Okay. Example number 1. This is also example number 1, but this is for time response. Example number 1 for the ODE. Okay. We already derived that, so I'm just going to. Okay, the first step is produce ODE. All right, you will do the free body diagram, determine the direction of the force. Okay, but basically what you get is you're going to get this ODE, md square x naught plus cdx naught plus kx naught equal to cdxi plus kxi. Okay. Okay, so we already derived in this example here, example 1. So I just take the derivation and we're going to use it straight away. All right, so right, so let's write d square x naught plus c over m dx naught plus k over m x naught equal to c over m dxi plus k over m xi. Okay, and then and then we're going to apply this value here, k over m equal to 2 and c over m equal to 3. Okay, so therefore we will get, okay, c over m is 3, okay, k over m is 2, this is 3, this is 2. Therefore we get d square x naught plus 3d x naught plus 2 xo equal to 3d xi plus 2xi. Okay. All right, and then second step, Laplace transform. Okay, Laplace transform. Okay, so we're going to convert the differentiation in the equation into the Laplace form. So here we can see that there is a second differentiation term, and here this is the first differentiation term. Okay, this one, another one. Okay, So you can just refer to the table. So if you have d square, it will become x naught s square x naught s minus, I think, minus s x naught 0 minus x prime naught 0. Okay. For single differentiation, it is x s s naught s minus s x naught 0. Okay, so we're going to apply that into the equation. Therefore, we're going to have okay, s square x naught s plus minus x naught s 0 minus x prime naught 0, that is for the second differentiation, plus 3 s x naught s minus x naught 0, that is for the second differentiation, plus 2x naught s, okay, equal to equal to 3 multiply with s xis, because this is for the input part, so we use xis, minus ini tak ada s, ni tak ada s lah. Okay, minus xi0 plus 2xis. Okay, so that is the Laplace form. Okay, then we do the third step, which is apply initial condition.
Doktor.
Yes.
Yang before equal tu plus 2 ke minus 2?
Plus 2. Sebab ni plus. Okay. Apply initial condition. Alright, so it is mentioned that it is mentioned that x naught 0 is 0, x prime 0 is 0, so this one is 0. Okay, for the input part, this will also be 0. Okay, because if we refer to the step input here, this input, step input there. Okay, if I draw it a little bigger. Okay. Okay. 1. So you can see that at time equal to 0, initially it is 0. Okay. Okay, so therefore the term here, this one also becomes 0. Okay, so therefore our equation will become s square x naught s, okay, plus 3s x naught s, okay, 3 dah habis, plus 2x naught s equal to 3s xis, okay, plus 2 xis. Okay. Alright, so plus itu lebih besar. Okay, so we're going to separate the output here. So we're going to factor s naught s multiply with s square plus 3s plus 2 be equal to 3s plus 2 multiply with xis. Okay. All right, so far? Okay. Saya sambung kat sini lah. Alright, so we have just now x naught s is equal to equal lah boleh tu. Berapa tadi? 3s plus 2 divide by berapa? S square plus 3s plus 2 multiply with xis. Okay, we just move s square plus 3s plus 2 to the other side. So now we have output, which is x naught s equal to transfer function multiply with the input. Okay. So what we're going to do is now step number 1, 2, 3, 4. Step number 4 is to apply input signal. Right, so we're going to apply the input signal. So the input is unit step input. Right, so in Laplace form, it will become 1 over s. Okay, I already explained about unit step input last week. Okay, from the table, for the unit step input, it is 1 over s. But if the unit is 2, that will become 2 over s. If the unit is 3, it will become 3 over s. Okay, so we're going to apply that. So therefore, the Laplace equation will become 3s plus 2, and then we can factorize that one become s plus 1, s plus 2. Okay, we can factor the equation s square plus 3s plus 2, it become that one, and multiply with 1 over s. Okay, this is the input, unit step input. Right, so therefore now our equation, okay, so this is the equation in Laplace form. X naught s equal to 3s plus 2 divide by s plus 1, s plus 2 multiply with the input 1 over s. Okay, so now let's do the step number 5, which is partial fraction decomposition. Okay, partial fraction decomposition. All right, let me share a table, partial fraction table. I'm going to share it on WhatsApp. Okay, mana? Okay, so I've shared on WhatsApp. Okay, there is a partial fraction, meaning from a function we can convert into partial fraction. So in our equation here, okay, our equation here, 3s plus 2 over s plus 1 over s plus 2 multiply with 1 over s. Okay, this term this term is equal to the function number 1. Okay, this is equal to function number 1. Okay, so therefore, in form of partial fraction, okay, function number 1 is referred to the table in the WhatsApp. Okay, so in partial fraction, it will become a over s plus b over s plus 1 plus c over s plus 2. Okay, so now this is in partial fraction decomposition. Okay. All right, so now we need to solve for A, B, and C. Okay, what is the value for A? What is the value for B? What is the value for C? For here, we're going to use reminder theorem. Okay. Okay, so reminder theorem. Okay, this is reminder theorem. Okay, so in order to solve for reminder theorem, the Laplace form equation will be separate into numerator and denominator. Okay, n is numerator, d is denominator. And that one is equal to the summation of partial fraction, which is we already transformed it just now. Okay, so for a reminder theorem, so in order to solve for any parameters, okay, for here it use A1, A2, A3, and A4, and etc. Okay, so in order to solve for A1, okay, you can see that we just take A1, okay, and then this term will be multiplied to here. Okay, and then we're going to consider S is equal to SI based on this function here. Okay, all right, so let's try on the example. Okay. Okay, so reminder theorem, right? So we have this is numerator over denominator. Okay, so now we're going to solve for A, right? So we're just going to take A here. Okay, so we write A is equal to S multiplied with this function here, right? So therefore we have 3S plus 2 divide by S plus 1, S plus 2, where we consider S equal to 0. Okay, because based on the term here, S there equal to 0 lah, S minus 0. Okay, so S equal to 0. Okay, so therefore we have this one here multiplied with S. All right. So this one can be cancelled. Okay, S cancel with S. Now we're going to replace S equal to 0 into the function. So this one will become 0. This one will become 0. This one will become 0. Okay. So therefore, A will equal to, 3 multiplied with 0 is 0 plus 2. So it is 2 divided by 0 plus 1, 1. This one will become 1. Multiply with 0 plus 2, 2. 1 multiply with 2, we got 2. So A equal to 1. Okay. Next is for B. Okay. For B, we're going to take this term. Okay, and then this term will multiply here. Similar step. Okay. So we're going to have B equal to 3S plus 2 divided by S, numerator, S plus 1, denominator, S plus 0. Okay, multiply with S plus 1. Okay, where we consider S equal to minus 1. Okay, because we consider this term here, S plus 1 equal to 0. So S equal to minus 1. Okay. All right, so we do the same. We're going to cancel. This term can be cancelled. Cancel this one. All right. And then we're going to apply S minus 1 into the equation. So this one will become minus 1. This one will become minus 1. And this one will become minus 1. Okay. So therefore, we will have B equal to 3 multiplied with minus 1, minus 3, plus 2, it is minus 1, divide by minus 1, multiply with, here is minus 1 plus 2, it is positive 1, multiply with minus 1 is minus 1. So B is 1. Check balik. Minus 3 plus 2 divided by minus 1 multiply with minus 1 plus 2. Okay, 3 plus 1 is minus 1 divided by minus 1 plus 2 is plus 2. So minus 1, 1. Right? So it is positive 1. All right, so try to do the same for C. Okay. Right, C will equal to numerator 3S plus 2 divided by denominator S, S plus 1, S plus 2, then multiply with the S plus 2. Okay, because here is S plus 2, so it will multiply with S plus 2. Okay, where we consider S equal to minus 2. Okay, again similar, S plus 2 equal to 0. So S equal to minus 2. Okay, so we apply the cancellation and etc. So we can cancel this with this one. Right, and then this one will become minus 2. This one will become minus 2. This one will become minus 2. Okay. So right, so we have minus 6 plus 2 divided by minus 2 multiply with minus 1. Okay, so therefore you get C is equal to minus 4 divided by minus 2. It is 2. Kata minus 6 plus 2 by minus 4. Positive one. Minus 1 betul. Minus 2. Okay. So minus 2 minus 2 plus 1. Minus 1. Okay. So please check. Sometimes I mix up. Okay. So it is positive 2. Okay. Therefore, our partial fraction will become, okay, so instead of using, now we're going to write x naught s is equal to 1, 1, 2. Okay. 1 over s plus 1 over s plus 1 plus 2 over s plus 2. Right?
Doktor, bukan negatif tu ke?
Alah, saya rasa macam negatif tu tapi saya tak, macam tak. Okay, positif. Sebab negative multiply with negative. Okay, positif. So therefore minus 2. Alright. Itulah saya rasa negatif tapi saya tak nampak tadi. Okay, so this one jadi minus lah. Okay, this one betul negative, negative. Okay, so now we're going to do step number 6, which is step number 6 kan? Step number 6. Okay, check lah 6 ke 5, 6 rasanya. Number 6 is inverse Laplace. Okay, so we're going to inverse Laplace. X naught s, okay, equal to Laplace in form 1 over s plus 1 over s plus 1 minus 2 over s plus 2. Okay, so therefore this one will become x naught t will equal to 1 over s. If we inverse, it will become 1. Okay. This can be seen in the table. Okay, so this is actually 1. So in Laplace form, it become 1 over s. So if we inverse back, so 1 over s will become 1. Right, and for the second term and the third term, the form is in this one. Okay, because we have 1 over s plus 1 and the other one is 2 over s plus 2. Okay, so here the form is s plus alpha. Okay, if we inverse, it will become exponent negative alpha. Okay, so therefore here alpha is equal to 1. Okay, so meaning if we inverse, it will become exponent negative, alpha is 1, so negative t. Right? And then for s, for 2 over s plus 2, it is equal to multiply with 1 over s plus 2. Okay. So again, we compare this term to the general term there. So therefore, alpha is equal to 2. Okay. So when we inverse to there, it will become exponent negative alpha 2 t. Okay. Alright. Right. So it become 1 plus exponent negative t plus 2 exponent negative 2t. Right? So that is the our time response, our equation for our time response, which is the solution for the Laplace form here. Right? So basically, this equation here, okay, we can use the equation here to plot, okay, to plot x naught versus t. Okay, so you can replace the t value here with t equal to 0, t equal to 0.5, t t equal to 1, t equal to 2, 3, 4, 10, infinity. Right? Any values actually. Okay, any values. Okay. So once you get the value, you can plot whether it will behave something like this, it behaves something like this, or it behaves something, maybe, I don't know. Okay. So in order to know the behavior, you need to calculate what is the value of x naught when t is 0, t 0.5, 1, 2, 3, 4, 5, 6, 7, 8 until infinity lah. Tak kisahlah sampai berapa tu. Okay. So that you can see the behavior of the x naught s after we apply the unit step input, meaning we just pull and then we stay at that position, and then we can see how x naught will change in time. Okay. So this is the function of time response analysis. Okay, any question related to partial fraction and also reminder theorem?
Doktor,
Yes, Zuhai.
saya nak tanya, kenapa xi0 is equal to 0 yang awal-awal tu?
Okay, like I mentioned, okay, let's plot this. Okay, so this is xi. Okay, this is t. Right. The signal is like this. It is unit step. Alright. So if the unit is like this, you can see here, because we want to get the x not 0, right? Because yeah, in this equation we require for s xi, xis minus xi0. Okay. Alright. Basically, it should give the value to you same like x not s. But basically, if you understand the unit step input, okay, but not all unit step input, but this one for unit step input with initial xi equal to 0, okay. So the signal is like this. So we can see here at x naught xi0, it should start with 0 initially. Initial condition before we apply the step input, the input should be 0. Okay. You may also have maybe you have something like this. Okay, so this is x naught 0 equal to, let's say this is 0.2. Okay, this is the initial condition if the step input is like this. Okay, meaning it start with some initial value. Okay, for a unit step input, normally it start with 0 unless it tell you. Okay, if it does not tell you anything, we're going to consider that the initial condition is 0. Okay, meaning any initial condition, whether it is for output and input, must be equal to 0. Okay, but if it mentioned to you like here xi 0 equal to 0.2, okay, so you can imagine that the signal is starting at 0.2 and then it increased by 1, so this one will become 1.2 because it is unit step input. Okay, and it stay at 1.2. Okay, so if it does not mention anything, just consider the initial condition is 0. Because if you have initial condition, the equation will become quite complex actually.
Faham, Doktor? Terima kasih, Doktor.
Yang ni only apply to unit step input je ke, Doktor?
Yang ni tu masuk apa? Ni tu apa?
Yang X xi equals to 0.
Si0. No. It's also applied to the RAM input. Okay, RAM input like this. Okay, so maybe your RAM input is starting like this. Okay, so this one, the initial is not 0. For this line, this is xi0 equal to 0. So it depends on the signal. Okay, basically for fundamental like this, we consider this for 0. But after this, for example, in your work later on, you're going to use this concept. You must understand that not all systems start from 0. So we need to know the initial condition. Okay, so by understanding the starting point here, okay, sometimes you have something start from here, but this one is also x naught. This is not x naught 0. This is xi. Let's say here is at 5 seconds. Okay, xi is 5 equal to 0. Okay, but for initial condition, it is at time equal
Doktor
to
tengok balik step nombor 6.
step number 6. Alright.
Macam mana yang last kali tu plus 2e tu?
Okay, because this term here. Okay, so we're going to separate 2 multiply with 1 over s plus 2. Right. This term will be exponent negative 2t. So it multiply with 2. So that's why it become 2 exponent negative 2t. Because exponent negative 2t is only for 1 over s plus alpha. 1 over s plus alpha. Okay, so that's why we separate.
Doktor, plus 2 ke minus 2?
Minus 2.
Minus 2.
Minus. Sorry, typo Okay. All right. Let's do example 2. Okay, let's do example 2. Okay, you can see here, the output is not starting at 0. Right? Okay, so we have s square ys minus s y0 minus y prime 0 plus 5 sys minus y0 plus 6ys equal to 12 exponent t. Okay, so exponent t in the Laplace form, if we refer to the table, okay, if we refer to the table, exponent t, okay, exponent t is this one. This one. This one. Okay, exponent negative t. Okay, so here exponent negative t, right? Therefore, the alpha is minus 1. Minus 1 tu yang tadilah. The alpha is 1 here, so that's why it become, meaning in general, it is exponent negative alpha t. Right? Okay. So if it is exponent negative t, so alpha is equal to 1. Right? But in our case, exponent t. Okay, so meaning here it is exponent negative 1 t. Okay, so therefore we consider alpha is minus 1. Okay, so if alpha is minus 1, the equation will become, in Laplace, it become 1 s minus 1. Okay, So we're going to apply 1 over s minus 1 into the equation. Right, so let's apply the initial condition. Okay, sy0 is 2 and then y prime 0 is 1. Okay, this one is y0 is 2. Right, and then this term here will become exponent t is equal to 1 over s minus 1. Right, so our equation will become s square ys minus 2s minus 1 plus 5s ys minus 10. Okay, 5 multiplied with 2. Right, and then plus 6ys equal to 12 multiplied with 1 over s minus 1. Okay, right, so we're going to write this again, s square ys. Okay, we have 5s and 5s there kan, s ys, okay, plus 5s ys plus 6ys. Okay, and then this one, this part here is minus 2s plus 11 equal to 12 over s minus 1. Okay, so basically we're going to separate ys. So we have we factor ys equal to s square plus 5s plus 6 equal to 12 over s minus 1 plus 2s minus 11. Okay, and then we have ys is equal to 12 plus 2s square plus 2s minus 11s plus 11 divide by s minus 1. If you're going to factor s square plus 5s plus 6, 3.2, okay, s plus 2, s plus 3. Okay, so going to leave us with 2s square minus 9s. Okay, ini tambah ke tolak? Cuba you checkkan saya punya darab yang di kat atas ni. Betul tak? Macam ada something wrong.
Doktor, minus 11 ke plus 11?
Itulah saya nak tanya. Minus 11 ke plus 11?
Plus.
This one plus?
To s plus 11. Minus 11, kan dia pindah kat sebelah. Minus 11.
Saya tengok negative plus. Di sini plus kan? Ke minus kat sini? Oh, sini dah minus. Sini minus. Okay, saya silap kat sini lah. Okay, here is this one is minus, right? Okay, this one will become plus. Okay, so here we become minus. Sekejap, patah balik. Ini betul. Ini S plus lah. S plus 11 minus 11. Alright. Okay, so therefore you're going to have 13S. Cuba bagi kat atas ni. Minus 11. Dua S square. Tolak 2S ni.
2S tu.
Tolak 2S. So sini jadi 9. Okay. Alright, macam tu kan? Yang atas. Alright, so divide by S minus 1, S plus 2, S plus 3. Alright. Okay. Alright, so if we refer to the table for the partial fraction, if you refer to the table, it will be function number 3. Right, so it will be function number 3. So for the step partial fraction decomposition, 2s square minus 9s minus 11 divide by s minus 1 s
Doktor,
plus, yes,
dia bukan 12 minus 11 ke? Yang jadi 1. Yang atas tu.
12.
Ya, kan ada 12 depan tu. So 12 minus 11.
Oh, 12 minus 11. 1 lah, kan? Cuba you check, cuba you buat sebab saya tak buat step by step. Minus 1 Yang lain dapat sama ke?
Plus 1 saya rasa.
Plus 1.
Betul.
Plus 1.
Plus 1
11S tu tolak 2S 9S.
Positif.
Positif.
Okay, positif. Alright. Positif. Sebab saya tak buat step by step, so tanda tu dah ni. 12 ni tertinggal kan? 12 tolak 11, 1 positif lah. So ini jadi positif. Okay. Alright, will equal to, okay, if you refer to function number 3, it is A over S plus 1 plus B over S plus 2 plus C over S plus 3. Okay. Right, so using reminder theorem, we're going to solve for A, B and C. Sebab tak muat, saya tulis kat sini lah. Okay. So reminder theorem for A. Okay, for A equal to berapa tadi? 2S square. Ah, 2S square plus 9S plus 1. Okay. 2S square, mana pula? Kita dah pas yang tu. Tak ada. Salah. Betul lah. Confused lah saya ni. Tengok balik. Okay, 2S square plus 9S. Betul lah tu. Okay. Okay, 2S square plus 9S plus 1 divide by S minus 1, S plus 2, S plus 3 multiply with A is over S minus 1 where we consider S equal to 1. Okay, so that is the reminder theorem. So we're going to cancel S minus 1 with S minus 1 and then we replace S equal to 1, S equal to 1, S equal to 1, then this one equal to 1. So therefore we're going to have 2 plus 9 plus 1. 9 plus 1, 10, 12 over 3, 4. So which is 12 divided by 12 is 1. Right? So similarly for B is equal to 2s squared plus 9s plus 1 divided by s minus 1, s plus 2, s plus 3 multiply with s plus 2. That is the denominator under B, where we consider s equal to minus 2. Right? So please calculate what you get for B. Then you do the same for C. Alright. So what would be the value for B and C?
Doktor, yang sebelum ni minus 9S ke? Macam minus.
Plus kot. Tadi kawan awak betulkan plus. Kan? Itu plus tu. Tadi kawan awak refer balik. Sebab saya tak buat step by step tadi. So ada miss, minus, positif, negatif semua tu. So yang 2s square plus 9s plus 1 ni kawan awak dah buat. So kalau awak tak percaya, awak check balik lah. Check balik dapat sama ke tak. So
Okay, doktor.
basically yang kawan awak buat dapat macam ni.
B3 C negatif 2.
Okay, B3 C negatif 2. Ada yang dapat lain ke? Okay, so tak ada. So meaning we write the equation. So ys is equal to 1 over s minus 1 plus 3 over s plus 2 minus 2 over s plus 3. Okay, so then we do the inverse Laplace. Put all the term here. Alright, so we get yt. Okay, 1 over s minus 1, it is exponent t. Okay, we already derived when we apply for the input just now. So exponent negative t, it will become 1 over s minus 1. Right, plus 3, 1 over s plus 2 is exponent negative 2t. Minus 2, 1 over s plus 3 is exponent negative 3t. Right? So that will be the solution for the Laplace form. Okay, which is also the time response. Okay. Any question? All right. All right. Example 3. Okay. Okay, example 3 is already in the x not s, meaning it's already in the Laplace. So this step is only, this example is only to illustrate to you on how to convert from Laplace form into partial fraction. Okay, but I already give you the table, so just refer to the table. All right, so for this one, what will become the partial fraction for example 3?
A over S plus B over S plus 1 plus C over S plus 2.
Yes, that is correct. C over S plus 2. Right? So you can refer to the table. So you can see that it's very much depend on the pembawah dia tu lah. As long as kat atas tu biasa 3S plus 2, maksudnya the function is common function without any S square or something. Okay, so we just take based on the because we be able to factorize S plus 1 and plus 2. Okay, basically this one may be in form of S square plus 3S plus 2. Okay, but since we're able to factor it, so we need to factor it. Okay, and then you're just going to solve for A, B, and C using a reminder theorem. Right? Example 3 is very basic, very straightforward because we already did all the step in the previous example 1, 2, and 3. Right, let's do example 4 here. Okay, if for example 4 here, we can see that we cannot factorize this. Okay, we cannot factorize S square plus 2S plus 5. Okay, you cannot get S plus 3 or S plus 6 or plus S plus 10 or you cannot factorize that. Okay, therefore, if you refer to the table, which function you're going to use?
5.
5.
Yes, function number 5. Okay, so it become A over S. Okay, the first form is S plus, so here we become BS plus C divided by S square plus 2S plus 5. Okay, so we're going to solve for A, B, and C. Okay, so here we cannot use the reminder theorem because we have three unknown, A, B, and C, but you just have two equation. Okay, so we cannot use reminder theorem. Okay, so instead we just going to use a comparison method. Okay, so we're going to expand this here. Okay, so you're going to have A multiplied with S square plus 2S plus 5, and then S multiplied with BS plus C divided by S square plus 2S plus 5. Okay, which is similar to this form here. S square plus 2S plus 5. Right? And then if you do the comparison, let's folder the equation first. Okay, we have okay, you can see this term here is equal to this term. Right? So we just going to let it be like that. Okay, we're going to consider this side to this side. Okay, so we just take the numerator here. Okay, because for the denominator is already the same. Right, so we're going to write 5 is equal to AS square plus 2AS plus 5A plus BS square plus CS. Okay, so we're going to have 5 equal to A plus B S square plus 2A plus C S plus 5A. Okay, so we're going to compare, because here, for this side here, this is actually 0 multiplied with S squared plus 0 multiplied with S plus 5. Okay, so we're going to compare that. Okay, we're going to compare that. A and B is 0 because we compare S squared to S squared. So the multiplier in front of S squared is 0. So we have A plus B equal to 0, right? And then this term here to 0. Okay. Second one is 2A plus C equal to 0. And then this term, okay. So 5A equal to 5. Okay, because 5A is the term without any S. Okay, it's equal to 5. All right, so therefore we can get A equal to 1. Okay, then we replace A to here. B equal to minus 1. Then we replace A to here. We're going to get C equal to minus 2. Okay, so the equation will become A over S kan. So we have ini apa tadi, X naught okay, X naught. X naught S is equal to 1 over S, okay, 1 over S plus BS minus BS plus C kan, BS plus C. Okay, so it become minus plus dulu nanti BS plus C, BS minus S minus 2 divide by term dia S square plus 2S plus 5. Okay, so you also can write X naught S equal to 1 over S minus S plus 2 divided by S square plus 2S plus 5. Right? So if you're going to inverse that, let's refer to the table. Yeah, let's write here. X naught S equal to 1 over S minus kenapa hilang tu tadi? Cuba refer balik, macam hilang dah. B1 betul lah tu, S plus tu. B1. S plus 2 divide by S square plus 2S plus 5. Right. So if we inverse the Laplace, so we get X naught T, okay, equal to 1 over S, it's 1, minus, okay, S square, okay. Since we don't have, I think we don't have anything similar to that, S plus 1, tak ada. Okay, so basically we need to manipulate the term here. S plus 2 over s square plus 2s plus 5. Okay, so we need to do some manipulation. Okay, so basically try to get whether in this form, this form, this form, or this form. I'm not sure this one. Okay, but basically we need to manipulate the term so that we become to a standard form. So basically we have something like this one. Okay, we have this one here. Right, so we have s plus alpha. So this one here, the term at the numerator. Okay, but we need to manipulate so it become s plus alpha square plus beta square. Okay, right. If you refer to that, let's write the general. S plus alpha divided by s plus alpha square plus beta square. This will be s plus 2 divided by s plus 2 square. Okay, so if you have s plus 2 square, so that one is s square plus 4s. 4s kan? Plus 4. S plus 2 square. Itulah 4s. Okay. So s square plus 2s plus 5. So ini ada 2s. Satu. Okay. Plus alpha square plus beta square. Sine cos. Saya pun tak ingat lah. You try to manipulate ni. S plus 2 dah tu. S plus 2 square plus 1. Apa jadi S plus square plus 1 square? 1 square 1 lah.
But what if
Yes, why?
what if we do completing the square for denominator?
Completing the square. Mana square mana? S plus alpha square.
Tak, yang denominator yang method completing the square tu. Is it possible to do it?
Basically, the objective is to get the same form as the standard form here. Okay, because we have s plus alpha. This is standard form, but our equation here, is s square plus 2s plus 5, right? Okay, which is there is no meaning we don't have any standard form for that function s square plus 2s plus 5. Okay, so the objective is to manipulate the function here, this whole function here. Okay, s plus 2 over s square plus 2s plus 5, to manipulate that function such that it will appear to any of the standard form. Okay, any of standard form here, this one lah. Okay, either it is 1 over s plus alpha, which is not in our case because we have something at the numerator. We have s plus 2 there. Okay, that is something. Okay, so that's why I choose this one, because we have the term s plus alpha. But I might be wrong. Okay, it might be this one or this one. Okay, so the objective is to manipulate so that we get the same function as, meaning if we manipulate s plus 2 over s squared plus 2s plus 5, okay, if we're able to manipulate to the standard form, it's maybe in terms of, let's say this one here. S over, actually tak mungkin lah, tak timbul. S square plus alpha square. Okay, meaning alpha, you need to determine the value of alpha. Then if after you expand it, it become similar to s square plus 2s plus 5. Okay, maybe you need to add more function because we need to manipulate it. Okay, and basically I don't remember. I already solved that one, but like I said, I don't have the solution, so I don't remember. But basically, you can solve for, you can get the standard form for this one. I remember it is, I'm not sure. Okay,
Doktor, kalau buat penyempurnaan kuasa 2?
Macam mana tu penyempurnaan kuasa 2? Ini naik atas kat sini. Is it?
Yang atas ni. Yang S plus 2S plus 5 tu buat penyempurnaan kuasa 2.
Maksudnya S plus 2 square. Right. Over.
Kejap saya try buat.
Dia boleh buat. Tapi saya tak ada solution dia. Saya tak ada solution dia. Okay, so basically dia boleh buat macam like I said just now, we need to manipulate. Okay, so okay, let's just leave this here. Okay, try to do that. Okay, to manipulate to get into a standard form. Okay, if I get the solution, I will share it with you. Right, but basically, in term of step for the time response, we're going to focus on the first and second step, which is ODE and the Laplace transform, right? And then we're also going to focus on the applying the input, which is you need to determine the type of input there, step number 4, I think. Okay, and then step number 5 for the partial fraction, that is purely mathematics. You need to know how to convert from the function into the partial fraction. Okay, since we already have the table, so just refer to the table, right? And then for the inverse Laplace, this is something that you need to manipulate a little bit in order to use the standard table here. Okay, as for the application, meaning in real application, okay, this is something that you're going to see. Okay, all right. But as for the course, meaning for exam purpose, test purpose, okay, so basically try to focus on the step number 1, 2, 4, and 5. Okay, basically you won't get any very complex function like this. Okay, but okay, it maybe can be. So you need to practice with the objective is to get as similar to the standard form here. Okay, so some of the function is quite complex, so we need to manipulate that. So it will become similar to the standard form here. Okay. All right. So again, we're going to stop for this part here. Okay. So basically, it's already we already cover for the time response, which is the first part of chapter 3. Right. All right. Okay. So we're going to focus a little bit on this time response here. All right. As I mentioned, time response is an analysis in order to know the behavior of the system when the time is changed. Okay, that's what we call time response. The response of the output respond to the input in time. Right. So basically, we're going to do the classification. Okay, we're going to do the classification because by knowing the group of control system, okay, we will be able to predict the behavior. Okay, so by knowing the order of the system, the class of the system, or the rank of the system, we will be able to predict the behavior. Right. So in order to do classification of control system, okay, in order to do the classification of control system, we're going to consider the open loop transfer function. Okay, so we're going to consider the open loop transfer function. Okay, before this, during block diagram manipulation, we said that if we have a block diagram like this, we can simplify that to become y over u is equal to kg over 1 plus kgh. Right. Okay. So this is what we call as closed loop transfer function. Okay. So closed loop transfer function is kg over 1 plus kgh. Right. Sometimes we use closed loop transfer function to analyze the system. Sometimes we use open loop transfer function. Okay, for example, for the time response, we use closed loop transfer function. Later in the next chapter in stability, you're going to use open loop transfer function. For the root locus open loop transfer function, Nikes and both all used open loop transfer function. Okay. So here for classification of control system, we also use open loop transfer function. So how to get open loop transfer function? Okay, so open loop transfer function is you're going to multiply the feed forward path. Okay, again for feed forward path, multiply with feedback gain. Here we have H here. Okay, right. So open loop transfer function. We don't call it y over u. Open loop transfer function just k multiply with g multiply with h in Laplace form. Okay, so it is actually any gain on the feedback loop, on the feed forward loop. Okay, like this one here, feed forward loop k and g. Then you multiply with the feedback transfer function, which is h. In this case, it is 1 lah. H is equal to 1. Okay, or you can see here the term is already in here. Okay, so closed loop transfer function is actually feed forward transfer function divided by 1 plus open loop transfer function. KGH is open loop transfer function. Right, so that is open loop transfer function. Right, So in order to classify any control system, we need to determine the open loop transfer function first, right? So normally you can see the transfer function is written in this form, okay? You can see the transfer function, whether it is open loop or closed loop, it will be written in S plus 1 over S plus 3, S plus 6. Okay, similar like you saw in the time response just now. Okay, sometimes you see in this form, sometimes you also see in, let's say it is 2 over S cubed plus 3S squared plus 6S plus 5. Okay, so it may be in terms of factorial, okay, S plus 3, S plus 6, or it may be in polynomial form, okay? All right. Right, so similarly, the above term is what we call as numerator. Bagian atas dia kan, pengangkat. And then denominator is for the bottom part. Okay, numerator and denominator. All right, so if you look here, okay, so there is M. Okay, M is order for numerator. N is order for denominator. Right? And normally N is always bigger than M. Okay. So now we're going to do the classification. We already have the open loop transfer function. We're going to do the classification. Okay, so the classification will be done based on order, based on rank, and based on class or type. Okay, so for the order, we're going to find the highest order of S at the denominator. Okay, for the order, we're going to look at the denominator, and then we're going to see what is the highest order. Okay, for example, this one here. Okay, we look at the denominator, bawah dia, and we look for the highest order. So the highest order is 3. So this system is a third order system, third order control system. Okay. The second one is based on rank. Okay, rank is equal to N minus M. Okay, N is the highest order for the denominator, and M is the highest order for the numerator. So we minus N minus M, we get the rank. Okay, so for this example here, N is 3, M is 0, because here S0 plus 2. So S0 is 0. Okay, so the order is 0. Okay, and last one is class or type. Okay, here this is a mistake here, so cancel this term here. Okay, because highest order of S at the numerator, this is actually M. Okay, so for class it is highest factorial of S at the denominator. Okay, so for class, we're going to look at the denominator, and then we try to look what is the highest factorial S that can we have. Okay, so based on this example here, okay, we look at the denominator. It is S squared plus 3S squared, S cubed plus 3S squared plus 6S plus 5. Okay, if you're going to factor the S, okay, you cannot factor the S because the last term is 5. Okay, so it is 0. Okay, the class is 0 because you cannot factor the S. Okay, for easier step, we just look at the last term here. Okay, if you have S square plus 3S, 2S square plus 6S only, we look at the last term, it is 6S, so to the power of 1. So therefore, the class is class 1. Right? So we're looking at the denominator and then look at the last term in the polynomial. Okay. So if the last term contain S, so look what is the order of the S there. Right? Right, let's do this example. Okay. Right, so we're going to classify the control system based on order, rank, or class, or type. Okay. So order, we look at the denominator, look at the highest order, which is 4. So the order is 4. It is a 4th order control system. Okay, rank, n minus n, where n is 4, m is the power of 1 here. Okay, m is 1, so it is rank 3. Okay, as for the class, we look at the denominator and then we look at the last term. Okay, it is s to the power of 1. So the class is 1, the order of s factorial, the highest order of factorial s. And if you factor this, you can get s cube 3s square plus 3s plus 1. Right? So the highest factorial is 1. This is the mean of highest factorial order. Okay. All right. For B, what will be the order, rank, and class? Do the same for C. Order, rank, and class. Anyone?
Doktor, untuk B dengan C ni, dekat denominator tu kena kembangkan ke untuk dapatkan dia punya order maksimum?
Boleh, nak kembangkan pun boleh. Tapi kalau awak nampak, awak boleh nampak lah 5 lah. Okay, so this one order 5. Kembangkan boleh, tak kembang pun boleh. Tapi as long as you boleh determine the highest order, should be okay lah. Tapi untuk selamat, you kembangkan supaya you nampak lah what is the highest order kan. Okay, rank is 5 minus 0 is rank 5. Class, what is the class? Class? Okay, 3. So you already factor there, 3. Alright. C, for C. Order is 1 and 2. So order is 3. Okay. Rank, 3
1.
minus 2. 1. Okay. Class. Class is one we need to expand that. S kuasa 3 campur S kuasa 2 campur 4S campur 2S kuasa 2 campur 2S campur 8. So basically class 0. Okay, because we have this term here. Okay, so that's how we do the classification. So in order, a common classification that we use is based on order. Okay, based on order. Okay, so in control system, we're going to discuss on first order and second order system. Okay, if you learn in instrument, you also learn about zero order, first order and second order. First zero order sensor instrument, first order instrument, and second order instrument, right? So by knowing the order of the system, we will be able to predict the behavior. Okay, for example, for first order system, when we talk about first order system, we will directly know that it will behave like this. Okay, maybe like this, maybe like this. Okay, there is some parameters that we help us to determine the final value, how fast it responds. Okay, so that will be discussed in first order system. Okay, as for the second order, we will know it will behave something like this or like this or like this. Okay, so there is some parameter to that we can check, and from the parameter we can predict the behavior. Okay, so by knowing the order of the system, by classify the system based on order, we will be able to predict the behavior of the system. Okay. All right, I think I'm going to stop here. Okay, because we only left a few minutes, so we don't have enough time to discuss on first order. So let's continue first order and second order on Thursday. Right, so with that, I end this session. Thank you. Assalamualaikum warahmatullahi wabarakatuh.
Terima kasih, Doktor.
Thank you, Doktor.
Sama.
Thank you, Doctor.